Thank you for coming to our talk. So my name is Asahara. I work at NEC Corporation as a chief software architect as well as a researcher. And this is Yoshiki Takahashi. He is a master course student of Tokyo Institute of Technology in Japan. And he was our internship student last year. So today, we would like to talk about our latest work on predictive modeling automation work. Okay. So let's sharing of this talk. Is it okay? No problem.
A few more percent, maybe 80% of the machines are moved. Now, I cannot give you the details of how many
Hello?
machines.
Okay.
Hundreds of thousands of nodes.
So this talk focuses on the problem of modern predictive modeling, which requires a massive number of combinations of experiments to explore the best predictive model. The number of patterns becomes more than 1,000 cases. 1,000 cases by combining the variety of machine learning implementations, type of predictive models, and hyperparameter combinations. So the journey requires much effort of well-trained data scientists and takes much longer time. So this is very annoying and tough work for ordinary enterprise companies. To address this issue, we are going to propose an automation framework for predictive modeling. Our framework automatically explores a diverse space of the parameter combinations and produces the best model in several hours. So it achieved a high speed explanation by leveraging Apache Spark and Hadoop, and it achieved a high accuracy by plugging in the variety of modern machine learning implementations such as XGBoost, TensorFlow, and scikit-learn. And one of the most significant point we will stress in this talk is that our prototype framework achieves a much higher computation performance than Spark ML Lib. So the speed finally achieved 13 times faster. So in this talk, we also introduce the technical challenges to achieve this high performance, as well as the background of our work, overview of the framework, and detailed experimental results to demonstrate the efficiency of our framework. Okay, so then let's move on to the explanation of the background of this work. So as you may know, predictive analysis using machine learning technology has emerged in many fields of enterprise applications. So it includes infrastructure, industries, retail and marketing, manufacturing, communication services, supply chains, and so on. So predictive analysis is now getting to contribute the growth of the revenue and customer satisfactions and the growth of the market in human society. However, modern predictive modeling has three challenges for most of business people, and it limits the capability of the field of companies. So first, only highly skilled data scientists can master the high performance machine learning algorithms and implementations, because the algorithm require the PhD class computer science expertise. So it's so difficult for ordinary enterprise companies to hire the tens to hundreds such talents and assign them to every business divisions. So now, currently, most of only big companies uses machine learning technology in very limited fields. So second, machine learning algorithms have a variety of parameters called hyperparameters to tune up the accuracy of models to fit the data. So then the tuning phase usually requires much computation power and it takes a long time. And also, efficient tuning requires a highly skilled and business-oriented data scientists. Third point is the difficulty of to choose the best machine learning technology to achieve the high accuracy. So in both academic and industrial societies, machine learning algorithms and implementations are continuously being published and the performance improvement is rapid. So then it results in the much work efforts to keep tracking the latest machine learning implementations and speed and spend much time on trial of them. Now, so our framework addresses these three challenge issues by automating the annoying process of predictive modeling. So our automation framework brings these three typical values to you. So first, our framework democratizes the predictive modeling from highly skilled data scientists to ordinary business people with standard statistics knowledge. So then, you don't need very detailed knowledge on machine learning algorithms. You don't need to understand the meaning of hyperparameters. So you don't need to think the search space and consider the search space of parameter tuning. Second, our framework can complete the predictive modeling quickly, especially the process of model selection. So by leveraging the high-performance computation capability of Apache Spark and Hadoop, so our framework searches the combinations of not only the hyperparameters combinations, but also the variety of machine learning implementations and types of predictive models. So then it produces the best predictive model in several hours. Third point is the easiness of integration of our framework with future developed machine learning implementations. So our framework is designed as open to typical design of machine learning implementations and algorithms. So by extracting the common functionalities for high-speed machine learning. So for example, distributed and parallel computation part, data accessor, and data preprocessing part. So then, we can, by using our framework, we can quickly receive the benefits from future developed machine learning implementations. Okay, so from now on, Yoshiki will take this talk, and he will explain the overview of the framework, design challenges and solutions, and experimental results. So yeah, please start it.
Hello, I'm Yoshiki Takahashi. I would like to talk more detail of this work. From now, let me talk about the design challenges and solutions of automation framework for predictive modeling. This slide shows high-level architecture of our framework. This framework aims to produce a best predictive model automatically only by providing data sets and evaluation criteria, which is like accuracy, precision, or recall. I will show the overall flow of our framework in this slide. First, it automatically generates many pairs of machine learning algorithms and its hyperparameter. Learning algorithms can easily be added to our framework, as we will talk later. Then, some third-party machine learning implementations parallelly run on Apache Spark or the configuration specified by that pairs and save the trained model on HDFS. Finally, all the trained models are validated on Spark, and the framework selects the best model based on the given criteria. As you know, the pipeline of Spark ML Reap, scikit-learn, hyperopt are also one of the frameworks of automated machine learning. We especially focus on quickly exploring a lot of possibilities of learning settings and easily adding new machine learning implementations. I'll show you about two design challenges of our framework. The first challenge is about scheduling to improve scale-out performance for enormous possibilities of learning settings. The second challenge is about software design to easily add third-party machine learning implementations to our framework. I think the techniques for these challenges can be applied not only to automated predictive modeling, but also to general purpose such as scalability in distributed processing and extendability of applications. So I'm glad if this talk has been useful for your development of Spark application. Now let me talk about first topic, scalability. First of all, just increasing the number of nodes and executing training in parallel does not improve the performance. For various learning settings, the execution time of training varies greatly, which is up to about 100 to 1,000 times. For various learning settings, the execution time of training varies greatly. As the upper nodes in this figure, where many training tasks with long execution time is allocated to one node, the other node, like lower node, have to wait for that node to complete the training. So the overall performance is affected to the upper node performance. As a result, adding nodes does not improve the overall execution time so much. Actually, this problem can be reduced to the combinatorial optimization problem and can be solved with several algorithms. First, let us assume that the execution time of each job, here the training task, is known. Then the total execution time can be calculated for any allocation patterns, which is max execution time of all nodes. We want to determine how to allocate tasks to nodes to reduce this total execution time. And this problem is known as a combinatorial problem called job shop scheduling. Generally, it is difficult to obtain exact solution because of the computational complexity. But an approximate solution can be derived by a method such as greedy algorithm. Actually, we use greedy algorithm to determine how to allocate tasks to nodes. However, there is one problem. In our case, how can we know the execution time of these jobs? The execution time varies depending on many factors such as learning algorithm, hyperparameter, data amount, and quality. Even if the learning algorithm and hyperparameters are the same, if the data is new, the execution time can also change. In our framework, the scheduler estimates the execution time of the job based on the results of profiling to several trainings on the sampled data. First of all, before the automated predictive modeling, it samples about several % data from the training dataset and executes some training tasks to that sampled data. For the case of a job using XGBoost, first it prepares several hyperparameter sets, each of which includes eta, max depth, round, and so on. Then it samples small data from the training dataset and runs XGBoost on the small sampled data for each hyperparameter set. The scheduler profiles a batch of training and runs execution time for an algorithm and a set of hyperparameter values. Now we employ a simple linear regression model for the scheduler to run an execution time. After the scheduler profiling, it performs scheduling for automated predictive modeling on the entire data. To achieve the jobs well balanced enough, how much data should be sampled and how many times running should be performed are important points of discussion. because we don't want to spend much time on the on pre-profiling. Actually, I will not deal with it in detail in this talk, but in our experiments, profiling takes little time to achieve high scalability performance efficiently. This slide shows pre-profiling tasks takes little time. This preliminary evaluation result is a case where data is sampled 1% for the pre-profiling, and training is run on same search space as automated predictive modeling. This figure shows the ratio of the pre-profiling time to the total execution time. The yellow hatched bar indicates the pre-profiling time, and orange bar indicates automated predictive modeling time. It is small enough to the overall execution time. So using 1% sample data for pre-profiling does not degrade the overall performance so much. Okay, now let me introduce the second technical point of our framework. The second point is about our software design to easily add third-party machine learning implementations to our framework. I will explain how to reduce the implementation cost to integrate our framework with a new machine learning implementation. First of all, we will assume that we incorporate a new machine learning implementation into these two main modules. The first is distributed training processing module, which performs multiple training processes on the available cores. The second is validation and model selection, which makes all trained models to perform predictions to the validation data and reduces this accuracy to select the best model. I will explain how to incorporate the new machine learning implementation into these modules. In naive implementation, the distributed learning module directly invokes the training functions of each machine learning implementation. For example, it calls a training function using XGBoost directly for a training setting of gradient boosting tree algorithm. However, with such a design, we have to add code to distributed learning processing each time we integrate with a new machine learning implementation. Encapsulating the training process makes the implementation easier. We create an abstract class of training task, and the distributed learning module invokes it. By doing this, the training process is encapsulated, which hides a difference in behavior between each machine learning implementation. As a result, implementers need to add a code to only training process using a new machine learning implementation. This also applies to validation. By encapsulating prediction process, implementers need to add a code to only prediction process using a new machine learning implementation. Okay, then let me introduce an evaluation experiment of our framework. This is an evaluation setup. We explored 864 grid points for the gradient boosting tree algorithm, 324 grid points for multilayer perceptron, which includes a network architecture as a hyperparameter, 5 grid points for logistic regression, and 18 grid points for random forest. We used Higgs dataset, which is table format data for binary classification problem, and sampled 1 million data for each training, validation, and test. Before executing automated predictive modeling, the scheduler preprofiles the same number of training tasks as automated predictive modeling using 1% sample dataset. This figure shows the completion time for the executions of our framework and Spark ML lib. The orange bar represents our framework, and the blue bar represents Spark ML lib, which explores the same grid points with 16 cores. Our framework has finished model search for 11 candidates in about 6 hours by running it in 32 parallel. While Spark ML Real spent 146 hours to finish automated predictive modeling, our framework finished in about 11 hours by running on 16 cores. So our framework achieves about 13 times faster. This result is reasonable because they focus on different problems for scaling out. Since Spark ML Real focuses on training on huge amount of data, it trains one model in data parallel using multiple cores. It reads the training dataset as a distributed data like RDD and splits the dataset to the multiple cores. Then it does shuffle operations several times to train one model. To explore huge search space of parameter tuning, it does shuffle operation repeatedly. Spark ML Real scales in the direction of the size of the data, but it does not so much scale in the direction of the size of the search space. On the other hand, our framework focuses on huge search space of parameter tuning. Each core is the entire data and trains one model locally. By doing this, each core can train models repeatedly without any shuffle or reduce operations. The more number of cores we use, the more models can be trained in unit time. That is scalable for the size of search space of parameter tuning. This figure shows the scalability of our framework. The x-axis represents the number of cores used for parallel execution, and the y-axis represents the processing speed if the speed with 2 cores is 1 as a reference value. This figure shows that our framework scales out with small loss. We may be able to reduce losses by using more sample data or various size of data for pre-profiling, rather than using 1% sample data. This shows error and AUC. AUC is one of the aggressive evaluation value. The predictive model obtained by running our framework achieves higher accuracy than the 3 algorithms run with default hyperparameters of XGBoost and scikit-learn. Since automated modeling also explores the default parameter values, it is natural for the accuracy to be higher than that. However, our framework achieved an important improvement of accuracy at least 0.013 points, and improvement of AUC at least 0.012 points to the default hyperparameters of each implementation. The strength of our framework is to produce prediction models with the best running algorithm and the best hyperparameter at any time for a variety of datasets. Finally, let's see the amount of code to plug in the machine learning implementations. We can plug in some machine learning implementations with less code. Since our framework is implemented in Scala, learning implementations supporting JVM APIs such as XGBoost can be plugged in easily. But other language API can also be added to our framework. Actually, TensorFlow and scikit-learn were implemented in Python. The reason why these code amounts are a bit more than XGBoost is due to the code for invoking Python process. Okay, let me talk about summary and future work. We talked about our latest work of automation framework to predictive modeling using Apache Spark. Our framework automatically explores the diverse paths of the parameter combinations and produces the best model in several hours. It achieves high-speed exploration by leveraging Apache Spark and Hadoop, and high accuracy by plugging in a variety of modern machine learning implementations such as XGBoost, TensorFlow, and scikit-learn. Our automation framework brings three technical values. First, our framework democratizes predictive modeling from high-skilled data scientists to ordinary business users with standard statistic knowledge. Second, our framework can complete the predictive modeling quickly, especially the process of model selection. Third point is the easiness of integration of our framework with future machine learning implementations. So we can quickly receive the benefits from future developed machine learning implementations by using the framework. And we address two technical challenges. First challenge is about scheduling for high scalability. And second challenge is about software design for open framework for machine learning implementations. In our future work, we are trying to improve data structure. In the current implementation, memory copy conversion is performed on common format dataset every training and prediction. While many machine learning implementations adopt original data structure for input data, our framework expresses data with a common format data structure. So it is necessary to convert it to these data structures at every training and prediction. This conversion involves memory copying, though it has not been measured yet. It is considered to degrade execution performance and memory usage efficiency. So it's better to use a common memory format that allows multiple machine learning implementations to read the dataset without memory copy. The topic on such a memory-aware data structure has become active recently, such as Apache Arrow. Apache Arrow is a platform that utilizes standardized memory format in several systems handling with different data structures. Since this activity is very close to our issue on data conversion, so we are paying attention to these technologies. If you have any ideas, please contact us after this talk. Thank you for listening.
Do you have any question?
Is this available? Is there a way to test this, use this? Is there code? Is there anything?
So sorry, so this is a proprietary software, so we don't disclose this implementation now. But well, we are challenging to publish the detailed technical information by publishing some papers, and we are planning to start this. So we are planning to develop some product or service to provide this technology to end users.
So as per my understanding, each algorithm is trained on a separate node in the cluster, right?
Yeah.
By randomly choosing or optimizing using some, linear programming method or dynamic programming method. I think you use to optimize the schedule on various nodes, right? The training.
So your question is some.
My question is, so how much data you are selecting actually, to train for each of that algorithm on a local node in the cluster? So how much are you selecting the complete data, or what percentage do you use to train the model on a single node?
So the question is so this architecture is obviously limited by the size of each node's memory, right?
Yeah.
So memory of each node. So how many samples can be used in the each parallel machine learning training?
Now it is limited to train the data. The size of it is limited by cluster memory, but we are trying to employ the data parallel machine learning to the in the future.
How many samples
How many samples?
are you using in the setting now?
In our experiment, we use 1 million samples was a data set.
That is not only the total size, but also the size for each node, assigned to each node. Right?
Yes, each node.
So 1 million. 1 million samples can be used in the training, for each training.
Yeah.
Yeah.
And are you using any other techniques to optimize the parameter selections, like simulated annealing algorithm or something like that, or are you evaluating each of the parameter combination there?
So what kind of somehow are you trying to how can I say use some clever or sophisticated algorithm for the scheduling part, dynamic programming, or some simulated annealing algorithm or something?
Scheduling.
Yes, not the scheduling.
For parameter selection.
Parameter selection. Parameter selection. Yeah.
Now, in this evaluation, we use grid search, but other parameter selection techniques, I think other parameter selecting techniques can be applied to our framework.
So now we don't use a very special or clever algorithm. So we just do the grid search of the combination of the parameters. But we may do some make it more clever or sophisticated algorithms. Yeah. Okay.
Sorry, are you using the ML pipelining at all?
But
As part of it, because I noticed you showed the scikit-learn, the random forest logistic regression, but those are implemented inside of the ML, and you could do pipelining to do the hyperparameters and stuff. Do you have any? Are you using it or compared that?
yeah, that's the question. So the question is, are you using some pipelines mechanism of each implementation, or some Spark ML lib or something, or you don't use the pipeline mechanism?
I don't use pipeline algorithm.
Algorithm implementation.
Implementations.
So you are using some scikit-learn pipeline or something?
In this framework.
Yeah, right.
In our framework, we don't use pipeline implementations.
So our framework, employs our own somehow kind of a pipeline mechanism to run a bunch of parameters, bunch of parameter combinations and predictive models and implementations. Okay. Any other questions? Okay. So thank you for listening to our talk.
Thank you
very much.